Hello, welcome to this lecture on modeling, analysis and estimation of three-phase unbalanced network. We are now talking about transformer modeling. So, in the last lecture, we have looked into the phasor diagram as well as the connection diagram for an YgYg0 transformer. So, we just for a very brief recollection, YgYg0 means that there is no phase difference between the primary side phasor voltage as well as the secondary side phasor voltage, and for this type of connection or rather any kind of connection, as we will show later on also, that there is a very simple method to find out the phasor diagram as well as the connection diagram. So, just for a very brief recollection, what we did, that we first took these three sets of transformers, indicated their dot positions, and then first we made the connections at the primary side according to our choice. So, here for example, we have taken A2, B2, C2 terminals together and then simply grounded them, and then from A1 terminal we said that it is phase A, from B1 terminal we said that it is phase B, and from C1 terminal we said that it is phase C. And then after that we have drawn the phasor diagram at the primary side, and then we have reflected these connections at in this particular phasor diagram of the primary side, that is. So, then therefore, here also as you can see that because here we have connected A2, B2 and C2 together and actually connected them to ground, and basically the same thing also we have reflected here. So, from terminal A1 we said that it is phase A, terminal B1 we said that it is phase B, and terminal C1 we said that it is phase C, and then A2, B2, C2 they are connected together and that is grounded. And then with this connection, so with this phasor diagram, then we have gone for the phasor diagram at the secondary side. Now, because here phase A and phase A of the secondary side, they are in phase. So, then therefore, of course, this phasor diagram would always exactly the same as that of the primary side. And we have said that because there is no phase difference, so then therefore, if this is A1 A2 terminal, so then therefore it will be also A1 A2 terminal, and then again it is B1 B2, so then therefore it will also be B1 B2, and if this is C1 C2, this one also be C1 C2, right. So, then therefore, here from here we can automatically see that here also what we have to do, that we have to tie up A2 B2 C2 together and let us say ground that particular node, and then from small a1 terminal we will take secondary side phase A, for small b1 terminal we will take secondary side phase B, and from small c1 we will take secondary side phase C. And then once we have made this terminal marking here, we come back here at this side, and then we simply reflect these terminals here. So, here also we do make A2, B2, C2 tied together and then simply ground it, and then from small a1 terminal we take it is phase A. So, this is phase A, and then from small b1 terminal we take phase B, and from small c1 terminal we take phase C. So, that is how we do make the connections. We will also look into some several more examples, so it will be more clear as we proceed in this course. Now, with this connection, now how do I proceed? Now, here we have to again understand some very simple thing, or rather it is a kind of, let us say, a recollection of a very simple thing. So, for this transformer, if I say that it has got the per unit leakage admittance is Z, per unit leakage admittance is Z. So, then obviously per unit leakage admittance is Y. So, per unit leakage impedance is Z. So, then obviously per unit leakage admittance is Y, Y is nothing but 1 by Z. And then because we have neglected, we have already said in the last lecture that our assumption is that we are going to neglect the magnetizing impedances of any transformer model. So, then therefore, for this transformer the model is very simple, it will be only represented by this, and this side is VA, voltage is V capital A, this voltage is V small a. So, in per unit, and then if I say that it is IA then of course I can write that IA is equal to Y into VA minus V small a. So what does it mean? So it is so then the current entering in the into the primary side is nothing but Y into the difference between the voltages at the two dot positions. So it is VA is the voltage at the dot position and V small is the voltage at the dot position. So it is the difference of the voltages at the two dot positions. So if I use the same principle here, so from here I can write down the same thing. So I can say now here, so IA would be Y into the voltage across the terminal A1, A2 is V capital A. So this voltage is V capital A, this voltage is V capital B, voltage is capital C, this voltage is V small a, volt small c, and this voltage is V small c, small b small c. So obviously, so from here I can see that the potential across the terminal A1, A2 is V capital A and the potential across the terminal small a1, a2 is VA. So then therefore IA would be nothing but VA minus V small a. Similarly, I capital B would be given by Y V small capital V minus V small b. Here please note that we have assumed that all these three single phase transformers are identical. So, all of them have got same Y values, that is the same leakage admittance. So, I mean that is also another kind of, let us say, tacit assumptions, and I capital C is Y to V capital C minus V small c. Now, as we also know that from the convention of the dot diagram that I capital A which is entering the dot position at the primary side would it be in phase with the current I small a which is going out of the dot position at the secondary side. And if the turns ratio is 1:1, so then obviously they would be of same. So here also let us assume that this turns ratio is 1:1 for the sake of simplicity, right? And of course, ideally any transformer can be of any ratings. For example, let us say 400 volt by 33 kV. That is, of course, I mean that is the basic objective of a transformer, to actually basically transfer the voltage from one level to another level, but then in per unit everything would be 1:1. So please note that we are doing all modeling in per unit. So therefore, in per unit all this ratio would be 1:1. So I capital is Y into VA minus BA. So that also would be is equal to I small a, because here you see I small a is going out. Similarly, I capital B is Y into V capital B minus V small b, that is also would be equal to I small b, because I small b is also going out of the dot position from the secondary side. And then I capital C would be also equal to Y into V capital C minus V small c, that is also would be equal to I small c. So you have got all the expressions of all the 6 currents in terms of 6 voltages. So now we have to put them together into a matrix. Now, so let us again write down the equations on the next slide. So I have that I capital A is Y into V capital A minus V small a is equal to, that is I small a, and I small b is Y capital V to V capital B minus V small b is equal to I capital B, I small b, and I capital C I small c. So from here obviously minus IA is y into, that is trivial, but let's just for the sake of. Right now, why we are doing it? Because if you remember, in the last lecture we said that for the sake of ease of modeling, or rather for the sake of incorporating the transformer model into the overall model of any large three phase transmission or distribution network, we need the model such that all the currents of the transformers are entering into the transformer. Now here at the primary side, as far as this connection is concerned, the currents I capital A, I capital B and I capital C, they are entering, but the currents I small a, I small b and I small c, they are going out. So then therefore, for the sake of modeling, I have to take these currents entering also at the secondary side. So then therefore, I have to model it as an equation where the currents, instead of taking to be I small a, I have to take it as minus IA. Similarly, for phase B, instead of taking it as I small b, I have to take it as minus IB, and for small c, instead of taking I small c, I have to take minus IC. So that is what we have to do, and so then therefore we have got all the equations. So now let us write down all the equations together in a matrix form. So what I have got is I capital A, I capital B, I capital C, minus I small a, minus I small b, minus I small c. We will write down the elements little later immediately, but let us first. So it is all or y, so we take y common, everywhere y would be taken common. So VA minus VA, so it is 1, 0, 0, then minus 1, 0, 0. Then YIB is y into VB minus VB, so 0, 1, 0, 0, minus 1, 0. I capital C is y VC minus VC, so it is 0, 0, 1, 0, 0, minus 1. And then minus I small is y into VA minus VA. So this is minus 1, 0, 0, then it is 1, 0, 0. Minus IB is y into VB, so then therefore 0, minus 1, 0, and then 0, 1, 0. And then minus IC is y into V small c minus capital C. So it is 0, 0, minus 1, 0, 0, 1. So that is it. So this is the 6 cross 6 matrix. So y into this. So you can see that it is a 6 cross 6 matrix. So what we do is now that we do partition it. So we do partition it. So this matrix is y1, this matrix is y2, this matrix is y3, and this matrix is y4. So matrix y1 is y into identity matrix, matrix y2 is y into minus of identity matrix, matrix y3 is y into minus of identity matrix, and minus y into identity matrix, and y4 is y into identity matrix. So this is a very simple one. and that's how we find out. So then therefore here, and then so from here, so I mean basically this is the model, so I can say that IABC is IY1 into VABC. So my model is complete. Y2 to VABC and IABC. I call this is equal to Y. So our job is done. So we have completed the model. Now here of course we IAB says of course, that is the definition we have used. Okay. So this is the process by which we find out. Now let us look at another example to make it more clear. Let us take an example. Let us take an example, say YgYg4, just to make the concept more clear. 4 means the phase differences, so x is equal to 4. So phase differences is equal to 4 into 30 degree, that is 120 degree. So that means that phase A voltage of the secondary side will be 120 degree lagging as compared to the phase A voltage of the primary side. So please note, when we are talking about YG, YGX or rather any transformer, say YDX, we always say that the secondary side phase A voltage is lagging with respect to the primary side phase A voltage with a phase difference of x into 30 degree. So that is the concept. So here how to go about it. So again we start with the same thing. So we first take three windings, so I again dot put the dots, say so I again put the terminals A1 A2 B1 B2 C1 C2 and also the terminal small a1 small a2 small b1 small b2 small c1 small c2. We have just taken the windings and then just mark the terminals and the dot positions. We have not done anything else. And after that, now we start doing the calculation. So YgYg. So this side is also grounded. So what I do is I simply ground it, and I say that this is phase A. I say that it is phase B, and I say that it is phase C. So again we have done the same thing. So we have basically tied the terminals A2, B2, C2 together, and then we simply take from A1 terminal phase A, from capital V1 terminal phase B, and from capital C1 terminal phase C. Now we draw the vector diagram. So we primary side vector diagram is always the trivial one. So ABC, say this is phase A, and so now this is, so again here I say that it is phase A, and the terminals marking are, we are reflecting these terminal markings here, so it is A1 A2, and we say that this is phase B, so this is B1 B2, and we say that this is phase C, terminal markings are C1 C2. Right. So here again we have reflected the same terminal marking. So here A2 B2 C2 are tied together and grounded, and from A1 we have taken phase A, and that is what exactly we have done. From capital B1 terminal we have taken phase B, and from capital C1 terminal taken phase C. I mean that is what we have exactly done. That is what we have just reflected. Now we have to draw the phasor diagram at the secondary side. So this is the dotted portions are the phasor diagram had there been no phase difference, but now phase difference is there. Now we say that but our connection is YgYg4. So that means the phase A voltage is lagging, or rather that means that the phase A voltage of the secondary side is lagging the phase A voltage of the primary side by 120 degree. So that means my phase, so these would be my phase A. So because this is, so now automatically this would be my phase B, 120 degree. Now these would be my phase C. You see, so phase A voltage of the secondary side, this is now lagging the phase A voltage by 120 degree, phase B voltage, and then automatically, and then of course phase B would be lagging phase A by 120 and phase C would be leading phase C by 120 degree. So once we locate phase A, automatically phase B and phase C, they are automatically located. Now the terminal marking. Now you see these vector and this vector, they are parallel. So then therefore, if these terminals are B1, capital B1, capital B2, so that means this terminal also would be small b1, small b2, right. This vector and this vector, they are parallel. So if these terminals are capital C1, capital C2, so this terminals must be small c1, small c2. And this vector and this vector, they are parallel. So then therefore, if it is capital A1 and capital A2, so this also must be small a1 and small a2. Writing was bad. A2. This is B2. And then because it is grounded, so this is grounded. So now this vector diagram and the terminal marking gives me the connection. So what does it mean? Again it says that from this vector diagram we find that what I have to do? I have to connect A2, B2, C2 terminals together and ground it. So I connect A2, B2, C2 terminals together and ground it. And then from terminal A1, I say that this is phase C. From terminal B1, I say that this is phase B, sorry, this is phase A. And from terminal C1, I say that this is phase B. Right? So this connection diagram is obtainable from this vector diagram. So it says that from A1, terminal A1, I will take phase C. So this is phase C. From terminal B1, I take phase A. So from terminal B1, I say this is phase A. And from terminal C1, I say take phase B. And that's what we have done. So please note that we are not making this connection diagram first. We are first making the connection diagram at the primary site according to our choice. Then I draw the vector diagram at the primary site. Then I reflect this connection terminals at the primary site. Then depending upon the phase difference given, then we draw the vector diagram at the secondary site, and then we locate the parallel vectors, and after locating the parallel vectors, accordingly we mark the terminals at the secondary site. And once we mark the terminals at the secondary site, from that terminal marking at the secondary site vector diagram, we make the connections. So it is not that we first make the connections and do the vector diagram. So it is basically interchangeable. So first primary site connection diagram, then primary site vector diagram, then secondary site vector diagram, and then secondary site connections. So that's how it proceeds. And this is very methodical. So here we really don't have to at all remember anything. So it is very methodical. So now what happens? So now of course, so now you see, so this current is I capital A, this current would be I capital B, this current would be I capital C. This voltage is of course VA. So this voltage is VA. This voltage is V capital B. This voltage is V capital C, and now this point potential is now Vc. This point potential will say that this is Va, and this point potential will say Vb. So then this is a current which is going in this direction. I would say that this is Ic, right? This current I will say that is Ia, and this current I will say Ib, because it is phase B, because it is phase A, because it is phase C, right? So that's how it is. So with this, now we can write down. So now here I can say that I capital A and I small c, they are in phase. I capital B and I small a, they are in phase, and I capital C and I small b, they are in phase, and V capital and VC. So now from here, how can I write down what is IA? As I said that the current IA would be nothing but Y into the difference between the voltages at the dot positions at the two sides. Now at the primary side the voltage is V capital A at the dot position, and at the secondary side the voltage is V small c. So then therefore IA would be Y into V capital A minus V small c. IB would be Y into V capital B minus, this is VA, so VA, and I capital C would be Y into V capital C minus V small b. So that is equal to IC, because these two are now in phase. Current entering at the primary side dot would be in phase with the current leaving the secondary side dot, I small c. IB would be, now from this connection I get I capital B would be is equal to I small a, and I capital C would be is equal to I small b. So these are the equations, right? So from these equations, so I can write down the, so now let us again, just for the sake of, so IA is y into V capital A minus V small c. So, that is equal to I small c, and I capital B is equal to y into VB minus VA, that would be IA, and I capital C would be y into V capital C minus VB. So, that would be IB. Right. So, then therefore, from this I can write down. Now, again we must notice that says this, that this at the secondary side all the currents are going out. I have to take them going in. So, minus IC. So, from here we will write that minus IC is y into V small c minus V capital A minus IB, sorry, minus IA, minus IA is y into V small a minus V capital B and minus IB is equal to y to V small b minus capital C. So, I have got 6 currents. So, then my model would be so the model would be, so IA is y into VA minus VC. So, V capital A minus V small c. So, y, because everywhere there will be y. So, 1 0 0 0 0 minus VC. So, minus 1. IB is y into VB minus VA. So, 0 1 0 minus VA. So, it is 1 minus 1 0 0. I capital C is y into V capital C minus V small c. So, 0 0 1 and 0 minus 1 0. Minus IA, minus IA is y into V small a minus V capital B. So, 0 minus 1 0 V small a 1 0 0. Minus IB is y into V small b minus V capital C. So, 0 0 minus 1 V capital C and VB 0 1 0, and minus IC is y into V small c. So, 0, sorry, VC minus V minus VA. So it would be minus 1 0 0 and VC. So, 0 0 1. So, this is the 6 cross 6 matrix. So, again we do the partition. Y1, Y2, Y3, Y4. So, this is the partitions, and if you can notice that Y2 and Y3 they are transpose of each other. Here you see Y2 and Y3 they are transpose of each other. Y1 and Y4 is of course identity matrix plus, but please do kindly note that it is not necessarily that y1 and y4 would be always transpose of each other. No, it depends on the kind of connections. We shall consider some of the other types of connections in our next lectures, in our, let's say, my future lectures. So, not necessarily that any of this matrix would be an identity matrix, not necessarily that y1 and y4 would be always an identity matrix. In the two examples which you have taken today, just to illustrate the process for an, let's say, YgYg transformer, y1 and y4 turns out to be the identity matrix, but it is not always necessary. Neither it is always necessary that y2 and y3 would only have, let's say, 1 or minus 1 at the entries. No, they can also have any other entries, but what would always remain the fact that y2 and y3, they would be always transpose of each other, right. So, that will always remain, and that we will see that it always holds good. So, here also we can take that IABC is equal to y1 into VABC and etc. So, basically that is why. So, that is how we do model, right. So, this is y1 matrix, this is y2 matrix, this is y3 matrix, y4 matrix. So, following the same process, we can do the modeling for any other types of YgYg transformer, that is YgYg2, YgYg6, YgYg8 and YgYg10. So, I am not going to do them here in this course. I invite you and I do suggest that you please kindly uh, do derive this transformer. It is very easy, it is quite fun, and uh, once you do this couple of exercises, you will be able to build the all kind of confidences as to how to model the YgYg transformers. Thank you so much.